Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
We've all seen the pictures from Mars, right? Those incredible rovers, Curiosity, Perseverance. They're just engineering marvels.
Absolutely. Peak technology, nuclear-powered, incredibly complex systems, some the size of a small car.
And the science they send back is, it's priceless. But there's always that but, isn't there? The cost is enormous. Billions of dollars.
That's one side, yeah. Billions per mission.
And the other thing is, they're slow. They cover ground really slowly. We measure their progress in, kilometers per year?
That's pretty much it. And that's the fundamental trade-off you make with that kind of traditional exploration. Right. You get incredible precision, amazing longevity at one specific spot, but you totally sacrifice scale. Our picture of Mars, the geography, the climate, it's been shaped for decades by what these very expensive wheeled robots can see right where they happen to be.
Which leaves a pretty big gap, doesn't it? What if you want to understand something huge like planet-wide climate patterns or, track geological features over hundreds, thousands of kilometers?
Exactly. A single rover, however advanced, just crawling along. It can't give you that big picture, that systemic distributed view.
Right.
And that's precisely why this other idea, the one we're looking at today, is, it's so radical, the Tumbleweed rover concept.
Tumbleweed, okay.
Yeah. The idea is basically to ditch all that complex propulsion, the motors, the heavy wheels, the nuclear core, and instead use the most abundant resource on Mars.
Which is the wind. You're
Yeah.
talking about these sort of spherical, lightweight things just getting blown across the surface, like giant planetary dandelions.
It's a pretty good analogy, actually.
Yeah.
And look, we've just gotten some really critical results back from wind tunnel tests, field tests. This isn't just some sci-fi fantasy anymore. It's quickly moving towards being a real possibility for future missions.
Wow. Okay.
So the really big question here is, how can a massive ball, we're talking 5 meters across, just pushed by gusts of wind, become this transformative technology? How does that let us explore Mars on a continental scale?
It sounds more like a giant, very sophisticated beach ball than a rover.
Well, it might look simple, but the science behind making it work is anything but. It seems simple, but it's actually more pragmatic and scientifically robust than you might think at first glance.
Okay, let's unpack this then, because it sounds like it relies on radical simplification, but that simplicity has to be grounded in some pretty solid physics, right?
Absolutely. Let's start with the machine itself.
Okay, define this Tumbleweed rover. Physically, what are we talking about? Size, construction?
Physically, yeah. They're designed as ultra-lightweight spheres. And the scale is, it's kind of astonishing. Fully deployed, the target size is 5 meters in diameter.
5 meters? Wait a minute. Perseverance is about 3 meters long. That's huge. Like giraffe height rolling on Mars.
Pretty much. Think about that visual. The structure itself is basically an advanced, very durable shell, maybe like a tough balloon, made from extremely light but really resilient materials. The whole design is about maximizing that surface area while keeping the mass incredibly low.
But why so big? Why 5 meters? Wouldn't something smaller be, easier to handle, easier to launch?
But the size is actually the secret sauce. It's directly linked to the challenge of moving anything in Mars's atmosphere.
Because it's so thin?
Exactly. Compared to Earth, Mars has almost no atmosphere, less than 1% of ours at the surface. So to actually catch enough wind to move,
you need a big sail.
You need a huge surface area for that thin wind to push against, combined with the absolute minimum possible weight. A 5-meter sphere seems to hit that sweet spot, that optimal ratio of sail area to mass. It gives you enough oomph, enough rolling torque from the Martian wind. It's all engineered around fluid dynamics in that specific environment.
Okay, so the entire mobility system is just harnessing Martian wind. Like you said, like the tumbleweeds we see rolling across deserts on Earth.
That's the model.
Which means you're basically swapping out the need for power sources. No complex motors, no RTGs.
Precisely. And that leads straight to the core goal, the really revolutionary part.
Yeah.
Large-scale and low-cost exploration. When you use the wind that's already there, you sidestep massive engineering headaches. Think about traditional rovers. They often rely on those RTGs, radioisotope thermoelectric generators.
The nuclear batteries?
Yeah, basically nuclear batteries.
Yeah.
Super high cost, very heavy, politically tricky to get approved for launch. By taking RTGs out of the equation, along with motors, complex gears, heavy wheels, the cost just plummets. The whole platform becomes almost disposable, relatively speaking. And that opens the door to mass production.
And if you cut the cost and complexity that much, suddenly you can think about not just sending one precious billion-dollar machine.
Exactly. You can employ the swarm strategy. The goal isn't one rover, it's deploying entire swarms of these relatively inexpensive rovers all at once.
A swarm! Okay, now that changes things. What's the scientific advantage of having a whole bunch of these rolling around?
That's where this mission concept really truly shines.
Yeah.
The scientific payoff of a distributed swarm. You shift from measuring things at just one point.
Like Curiosity does now.
Right. To systemic distributed sensing. The strategy allows for an unprecedented simultaneous view, as the team puts it, of atmospheric and surface processes from different locations on Mars. We could track dynamic things happening across the planet that are basically invisible to us right now.
That distributed sensing. Yeah, I can see how that's a game changer, especially for climate science, maybe large-scale geology too. What kind of questions could you actually answer with, say, dozens of these spread across a continent, things we just can't tackle now?
Okay, think about planetary climate modeling.
Yeah.
We know Mars has these huge, sometimes planet-encircling dust storms, right?
Yeah, the massive ones.
And powerful atmospheric pressure waves, sort of like big weather fronts moving across Earth. With one rover, like Perseverance, you can see a wave pass over you. You get a snapshot in time at one place.
Right.
But imagine you have 50 tumbleweeds spread out over 1,000 kilometers. Suddenly, you can map the pressure gradients, the temperature changes within the wave simultaneously. You can track its speed, how it evolves, in real time across a huge area.
Wow.
That's just impossible with single-point sampling. Or think geologically. A swarm could give you statistical data on soil composition or magnetic fields over a vast region. You move beyond just finding one interesting rock. You start understanding planetary scale trends.
Okay, so the rolling phase is obviously crucial for spreading them out and gathering that kind of data. But you mentioned there's more to it. The mission isn't just about rolling.
That's right. And this is where it gets, as you said, really interesting. The rolling is the deployment method, getting the instruments distributed across strategic target areas. But once they reach those spots, maybe pre-planned zones or areas of interest identified during the traverse, they stop rolling. The plan is for them to actually collapse into fixed positions.
Collapse?
Yeah, they transform into permanent measurement stations dotted strategically across the Martian surface.
Hold on. How does a 5-meter lightweight ball just stop and anchor itself? Does the source material give any clues about that mechanism? How do you deflate it or stick it to the ground?
That specific mechanism, the how, is likely still part of the team's ongoing development, probably proprietary at this stage. But the core concept involves a controlled deflation or maybe retraction of that outer shell.
Okay.
The key is that the interior payload bay, the part with the actual science instruments, needs to be secured to the ground somehow. This transition from mobile to static is absolutely essential for the long-term science value.
So they become little weather stations or something like that?
Exactly. Or seismic stations, radiation monitors. Yep. They can provide sustained measurements from fixed points over potentially years, tracking atmospheric pressure changes, temperature cycles, maybe detecting Marsquakes, monitoring radiation levels long-term. They can form a kind of data backbone across the planet.
Or even communication relays for other future missions.
That's definitely a potential application.
Yeah.
So yeah, the movement phase is the deployment strategy, getting them spread out. But the static phase is where you get that really long-term scientific return on investment.
Okay, the concept is, well, it's brilliant. But the practical side still feels daunting. We established Mars's atmosphere is incredibly thin. Trying to roll a giant, super lightweight ball in that low pressure, even with strong winds, it feels like it needed some serious proof, hard evidence.
Absolutely essential. You can't just assume Earth physics scales directly to Mars, especially with atmospheres. The scaling factors are notoriously tricky. So yes, the source material details 2 main experimental phases that have now provided that crucial proof of concept.
Right, the tests. Let's start with phase 1. That was the wind tunnel physics, right? July 2025. At Aarhus University's Planetary Environment Facility. They basically had to build a little piece of Mars on Earth.
Pretty much. They used scaled-down prototypes for this, specifically models with diameters of 30, 40, and 50 centimeters. They put these inside a special wind tunnel chamber.
And the key was the atmosphere.
The absolute key. The tests were run under a very low atmospheric pressure, 17 millibars.
17. Okay, remind us, Earth's atmosphere at sea level is?
About 1,013 millibars. So 17 is less than 2% of Earth's pressure. It's practically a near vacuum environment.
Why is simulating that low pressure is so vital, and I imagine technically quite hard to do?
It's vital because the way air interacts with the surface, the whole fluid dynamics picture, changes dramatically at such low pressures. Air becomes highly rarefied. How wind actually pushes the sphere, how the sphere interacts with the ground through that thin air.
Yeah.
It's just fundamentally different physics than here.
Okay.
If the rover design can roll efficiently at 17 millibars, it tells you the basic aerodynamic and structural design works for Mars. And yeah, maintaining that low pressure while also generating controlled wind inside a chamber is definitely a technical challenge.
Did they just test it on a flat surface?
No, that was another critical part. They ran tests over 5 different simulated Mars terrains, things like smooth plains, rough rocky areas, fine sand, surfaces with pebbles, even simulated boulder fields. They wanted to make sure it wasn't just a concept that worked on a perfectly smooth lab floor.
Right, because Mars isn't smooth, and the goal is to find that magic number, right? The minimum wind speed needed to actually get these things rolling consistently across different terrains. What did they find?
The results were really positive and remarkably consistent across the different setups. They found that sustained wind speeds of 9 to 10 meters per second were enough to set the models into continuous motion.
9 to 10 meters per second? Okay, is that fast? Like hurricane speeds?
Not hurricane, no. On Earth, 10 meters is about 22 miles per hour. A strong breeze, maybe a moderate gale. But remember, on Mars, the air is so thin, you need that speed to get enough force.
And that threshold, 9-10 meters, it worked even on the rough terrain, the pebbles, the boulders.
That's what they found. It held true across all those Mars-like terrains they simulated, which is a huge finding. It proves the basic mechanism is robust. It can handle different geological settings you'd expect to find on Mars.
Okay, so it rolls, but that's only part of the puzzle. If this thing is tumbling end over end, how does the science package inside stay working? Can it even collect accurate data while it's bouncing around?
Great question. And that was the other major validation for the wind tunnel tests.
Yeah.
They had sensors on board the prototypes, and yes, they successfully recorded data even during that vigorous tumbling motion.
Okay.
And maybe even more critically, the actual physical behavior of the rover, how it accelerated its rolling speed, how it reacted to wind gusts. That behavior closely matched the complex computer models, the fluid dynamics simulations the team had previously developed.
Why is matching the models so important? Is it just about proving their math was right?
It's much more profound than just checking the math. It validates their ability to reliably predict where these things will go.
Ah, okay.
Think about it. If you're mission control trying to manage a whole swarm of these things being blown around by the wind, you can't just rely on luck. You need high-fidelity predictive model.
Right, you need to know roughly where they'll end up.
Exactly. The Argos results basically proved that the physics engine they're using to calculate, okay, if the wind blows this way tomorrow, where will Tumbleweed number 7 likely be? That engine is accurate. That's absolutely fundamental for planning a mission, for coordinating the swarm, for actually achieving the science goals.
Okay, prediction is key. Now another practical thought. Mars isn't flat. It has hills, slopes, crater rims. A strong wind might push you up a gentle slope, maybe? But what happens if the terrain gets steep? Can a wind-blown ball actually climb uphill?
That was a specific thing they tested in Argos. And the results were pretty impressive. The scaled models showed they could climb a slope of 11.5 degrees inside that low-pressure chamber.
11.5 degrees.
Now, because of the differences in gravity between Earth and Mars and that low atmospheric density, they calculated that climbing 11.5 degrees in the chamber is equivalent to climbing roughly a 30-degree slope on the actual surface of Mars.
30 degrees, seriously, that's incredibly steep for any vehicle, let alone one that doesn't have powered wheels or direct steering.
It is. It really pushes the boundaries of what we thought possible for passive mobility. And it dramatically increases the amount of Martian terrain that would theoretically be accessible to these rovers. Fewer places they could get permanently stuck.
That's a big deal for mission planning.
Huge. And get this, the lead scientist, Mario Yuazo Carvalho de Pinto Balsamaso, he noted that these results are probably conservative.
How so?
Because the small prototypes they used in the wind tunnel, they were actually deliberately made heavier relative to their size than the final full-scale 5-meter rover is designed to be.
Ah, so they were testing a harder-to-move version.
Exactly. If they had perfectly scaled down the weight-to-surface area ratio, The actual threshold wind speed needed to get the real thing rolling on Mars might be even lower than that 9-10 meters per second they measured.
So the real rover might be even more responsive to the wind than these tests showed.
That's the suggestion, which is very encouraging.
Okay, so phase 1 in the wind tunnel nailed down the physics, the mobility threshold, the slope climbing, and validated their predictive models. What was phase 2 about? That moved things out of the lab, right?
Right. Phase 2 is about real-world operational data gathering. This was the field campaign back in April 2025. They took it to an inactive quarry in Maastricht in the Netherlands.
Quarry, why there?
Good analog for rough, rocky, irregular terrain. More realistic than a controlled lab surface. And for this test, they used a larger prototype, a 2.7-meter diameter version called the Tumbleweed Science Testbed.
So bigger, closer to the real scale. And the focus here wasn't if it rolls, but could the electronics survive and work?
Exactly. The primary goal was proving that the internal science package, the electronics, could not only survive the chaotic tumbling motion over natural ground, but also gather clean, usable scientific data while tumbling.
What kind of instruments did this testbed carry? Was it just dummy weight or actual sensors?
Actual sensors. It had a modular payload bay designed to fit standard, off-the-shelf components, which helps keep costs down too. For this test, it carried a camera, a magnetometer for measuring magnetic fields, a GPS, obviously for tracking its path on Earth during the test, and critically, an inertial measurement unit, or IMU.
Okay, an IMU. On a normal rover, that helps with navigation, knowing its orientation precisely. But what does an IMU do inside something that's constantly spinning and tumbling? Seems like it would just be chaos.
Well, the IMU is maybe the most critical piece for getting good data in this unique situation. It measures the rover's acceleration and its angular velocity, basically. It tracks exactly how fast and in which direction the sphere is rotating at every single moment.
Okay.
With that raw motion data, the onboard computer can then mathematically compensate for the spin. It can essentially de-spin the readings from the other instruments.
Ah, so it lets the camera take a stable picture or the magnetometer get a consistent reading even while the whole thing is rolling.
Precisely. It allows you to extract stable, scientifically meaningful data streams from the chaos of the tumbling motion. And the Maastricht test confirmed it worked. The platform successfully gathered and processed environmental data in real time while tumbling over that rough, natural quarry terrain.
Okay, so we have proof. They can roll if the wind hits 9-10 meters per second. They can climb surprisingly steep slopes. And they can actually collect scientific data while they're rolling. That brings us back to the big question about the fuel source. You mentioned earlier near-surface winds on Mars. We don't actually know that much about them.
That's been the historical challenge, yes. Our understanding is patchy. Near-surface winds are officially described as not well understood. Why? Because most of our data comes from landers or rovers.
Which tend to land in relatively safe, calm areas.
Exactly. We pick landing sites for safety primarily, not necessarily because they're the windiest places on Mars. So our data has been sparse and localized.
That sounds like a potential Achilles heel for the whole concept, doesn't it? Relying entirely on a power source that we admit we don't fully understand.
It definitely would be, except for some more recent data that's come in from, let's say, non-traditional wind sensors. And this new data really seems to bolster the tumbleweed idea quite significantly.
Oh, like what?
Well, NASA's InSight lander, for instance. Its main job was seismology, listening for Marsquakes. But its seismometer was so sensitive.
It kicked up vibrations from the wind.
Exactly. It recorded ground vibrations generated by the wind blowing across the lander in the surface. And it did this for over 2 Martian years, giving us a much longer baseline of wind activity at one location.
Interesting. Any other sources?
Yes, and perhaps even more directly relevant.
Right.
Measurements taken during the flights of the Ingenuity helicopter.
Ah, the little drone.
Yeah. As it flew, its sensors gathered data on air density, temperature, and wind speeds much closer to the surface than orbiting satellites can measure. And what both InSight and Ingenuity showed was that higher wind speeds, the kind Tumbleweed needs, seem to occur near the surface surprisingly frequently, more often than the older, lower average speeds typically reported.
Okay, so we're getting better evidence that strong winds near the ground aren't just rare flukes, they might be a regular part of the Martian weather cycle. How does this new data line up with that 10 meter per second threshold they need?
The analysis, particularly of the InSight data by Mario's team, is really encouraging. They suggest that, especially in Mars's northern hemisphere during its summer season, the daytime wind speeds show a wide distribution, but it's skewed towards those higher speeds needed. Around 10 meters per second isn't uncommon during the day.
So it's like a reliable daily power source during summer days.
That seems to be the pattern. And interestingly, even the nights, which are generally calmer, aren't always dead calm. They found that sometimes, even at night, speeds can spike above 10 meters per second, maybe due to atmospheric shifts or cold air drainage winds flowing down slopes or canyon walls.
Okay, so the fuel seems to be there, and maybe more reliably than we used to think. That's great news for planning a mission. Now let's get to the numbers that really show why this is such a different approach. The range. If you take that Aarhus wind tunnel data, feed it into their validated prediction models, what kind of distances could these things actually cover on Mars?
This is where the sheer advantage of just letting the wind do the work becomes incredibly clear. Their models predict that an average tumbleweed rover, just following the typical daily shifts and day-night cycles of the Martian wind, it could travel about 422 kilometers over 100 Martian sols.
422 kilometers in 100 sols. Okay, sol is a Martian day, just a bit longer than ours.
Right, about 24 hours and 39 minutes. So 100 sols is roughly 3 Earth months.
Okay, let's put 422 kilometers in 3 months into perspective. How does that compare to, say, Curiosity or Perseverance?
It absolutely dwarfs them. I mean, think about Curiosity, the gold standard, landed in 2012. It took over a decade, 10 years, to drive a total distance of just over 30 kilometers.
30 kilometers in 10 years. Wow.
Perseverance is on a similar track, measured in tens of kilometers total traverse so far. This tumbleweed concept is projected to cover more than 10 times the distance Curiosity managed in its entire mission in just the first 3 months.
That's a completely different scale of exploration.
It's moving from a slow, methodical crawl in one small area to potentially widespread, almost regional or continental coverage. That's the technological leap here.
If you break down that 422 kilometers in 100 sols, what's the average speed? Must still be pretty slow overall.
The average overall speed works out to about 0.36 kilometers per hour. Yeah, it sounds slow if you think about a car.
Right.
But the key thing to remember is that speed is sustained whenever the wind blows adequately. It requires no fuel from the rover itself. It only stops when the wind drops below the threshold. It's persistent.
Okay, so 422 kilometers is the average prediction based on typical wind cycles. What about the best case scenario? If you get lucky with strong, consistent winds blowing in the same general direction for a long time, what's the maximum potential range?
According to their modeling, under those ideal conditions, favorable terrain, sustained strong winds, the maximum potential range is just staggering. A single tumbleweed rover could potentially traverse as much as 2,800 kilometers.
2,800 kilometers? That's like driving from Chicago to Denver, or maybe halfway across the U.S.
It's enormous. We're talking about the potential to map geological changes, atmospheric phenomena across entire vast regions of Mars that are currently completely inaccessible to us, all powered by nothing more than the thin Martian air. It really opens the door to true continent-scale exploration.
That 2,800 kilometer figure, wow, that really sells the vision. So who's behind this? Who's the engine driving this, well, pretty bold, high-risk, but potentially very high-reward idea?
The group is called Team Tumbleweed, and they're specifically described as an interdisciplinary group of young entrepreneurial scientists. Their structure kind of reflects the whole low-cost, high-impact vibe of the project itself.
Young and entrepreneurial often means agile, quick to adapt. And you mentioned they're international.
Very much so. Which definitely helps when you're tackling a complex, multifaceted problem like this. While the main hubs seem to be in Vienna, Austria, and Delft in the Netherlands, the team actually brings together people from over 20 different countries.
That's impressive. That global collaboration must be key for pulling together expertise in, what, atmospheric physics, material science, robotics, software?
All of the above. You need all those disciplines working together simultaneously to make this concept fly, literally.
Okay, so they've proven the basic physics works. They prove mobility in simulated Mars conditions. They prove they can collect data while tumbling. What are the next big steps? What do they need to do to get this platform from, say, a working prototype to something genuinely flight-ready?
The main goal now is moving up the ladder of technology readiness levels, or TRLs.
TRLs, right? That's the standard scale NASA and ESA use to gauge how mature a space technology is, isn't it? It goes from 1 to 9.
Exactly. TRL-1 is just basic principles observed. TRL-9 is flight proven on a successful mission. These recent tests, the wind tunnel and the Quarry field test, have likely pushed Tumbleweed into the mid-level TRLs, maybe TRL-4 or 5 validation, in a lab or relevant environment.
Okay.
To get to flight readiness, say TRL 7, 8, or 9, they need to push forward on primarily 2 tracks now.
Track 1, I'm guessing, is making those prediction models even better. Since you can't steer it, you absolutely have to know where it's going.
Precisely. They need to keep refining those rover dynamics models. The real challenge is modeling the chaotic nature of Martian wind accurately. You've got turbulence, unpredictable gusts, maybe small dust devils that could knock it off course, terrain features like canyons or large dune fields that could block it or channel the wind in unexpected ways.
Right.
Mission control needs models sophisticated enough that they can feed in the latest wind data, maybe from orbiters or other assets, and get reliable trajectory predictions, hours, maybe even sols, in advance. That's essential for coordinating the swarm and making sure they actually hit their scientific targets.
What happens if one does get stuck, rolls into a deep crack or gets wedged in a really dense field of boulders? There's no way to drive it out. How do they handle that inevitability?
That's the inherent risk, and the operational philosophy has to accept it. There's no rescue capability, like with a wheeled rover. So the mission relies on 2 things. First, that surprising 30-degree slope climbing ability we talked about that significantly reduces the chances of getting permanently stuck in many types of unfavorable terrain.
Okay, makes it more robust.
Second, and maybe more importantly, the swarm strategy itself provides redundancy. Because each rover is relatively low cost. If 1 or 2 out of a swarm of, say, 20 get incapacitated, it's not mission failure.
It's an acceptable loss.
Exactly. The overall mission continues with the remaining units. The low cost allows for a higher tolerance for individual unit failure compared to a single billion-dollar asset.
Okay, so refining prediction models is track 1. What's track 2 for reaching higher TRLs? Integrating better instruments.
Yes. Moving beyond the foundational sensors like the camera and the IMU that they used in the testbed, the next phase is about integrating more specialized, science-focused instruments into that payload bay. Instruments that really leverage the fact that you'll have many of these spread out.
Like what specifically are they looking at?
They're focusing on things like advanced radiation sensors to map radiation levels across different latitudes and terrains, specialized soil probes, maybe something that can be quickly deployed or inserted into the ground when the rover naturally pauses for a bit.
Ah, interesting. Like a little quick sample.
Maybe. And also highly sensitive dust sensors. Given that the whole vehicle relies on atmospheric dynamics, and Mars is famously dusty, understanding dust transport and properties across wide areas is crucial. These instruments make the platform much more scientifically potent.
More sophisticated instruments.
Yeah.
Better models. That brings us to the next big test, doesn't it? The final, really critical field test before they can claim high TRL status. They're going somewhere very specific, very Mars-like.
That's right. The next major field campaign is scheduled for November, and it's taking place in the Atacama Desert in Chile.
The Atacama. Yeah, that's famous for being one of the best Mars analog environments on Earth, isn't it? Super dry, high altitude, intense UV.
Exactly. It's about as close as you can get to Martian surface conditions without leaving the planet. Ideal for pushing the system to its limits.
And what's the main goal in the Atacama? It's not just about proving one rover can roll again, right?
No, this is a systems-level test. The plan is to deploy at least 2 of the Tumbleweed science testbed rovers simultaneously, and significantly, they'll be carrying instruments provided by researchers from external partner organizations.
Oh, interesting. So other science teams are starting to buy in, wanting to get their instruments on this platform?
It seems so. That's a really good sign for the project's credibility within the wider planetary science community. But the absolute key objective in the Atacama, the thing they really need to nail down.
The swarm.
Yes. Operationalizing the core concept, the swarm itself.
Testing how multiple wind-blown balls coordinate with each other. How does that even work?
That's what they need to figure out and demonstrate. The primary goal is testing and validating the swarm coordination strategies in that realistic, harsh, Mars-like environment. This involves some pretty complex software and algorithms. How do 2 or more rovers, constantly moving semi-randomly based on the wind, maintain communication links?
Yeah, how do they talk to each other?
How do they coordinate their science? For example, can mission control instruct one rover that happens to be in an interesting spot to try and stop or slow down to take a soil measurement, while another nearby rover keeps rolling to track an incoming weather front? Can they relay data between themselves to get it back to an orbiter?
So it's moving way beyond just a single tech demo. It's about proving they can operate as an intelligent, distributed network.
Precisely. Autonomous coordination. That's the final piece needed to show this is a viable, functional, scientific exploration strategy ready for space.
So they're really ticking the boxes. Mobility proven. Data integrity while tumbling proven. Wind availability looking more promising. Slope climbing capability demonstrated. And now, the final hurdle. Autonomous swarm coordination in a Mars-like place.
That really is the comprehensive arc of the validation process they've undertaken. It's fascinating, isn't it? The core idea is so simple, let the wind push it, but making it actually work reliably as a coordinated scientific tool requires this incredibly complex, highly specialized software and system design to manage the inherent chaos of the environment.
It really is a remarkable achievement just to get to this stage. All this experimental validation, it feels like it successfully dragged the tumbleweed concept out of the realm of, cool idea and into something measured, practical, application-focused. They've shown the mobility works, they can survive steep slopes, they can get real-time data, all using Martian wind.
Yeah, I think this project really signifies a potential shift, maybe a fundamental one, in how we think about exploring planets. We could be moving away, or at least augmenting, the traditional model, centralized, very high-cost, slow-moving platforms, towards methods that are inherently cheaper, much more extensive in coverage, and actually use the planetary environment itself for mobility.
Right.
It just completely redefines what parts of Mars we consider accessible. The tumbleweed is kind of a testament to the idea that sometimes the biggest breakthroughs come from embracing radical simplification in the core engineering, even if the supporting systems get complex.
So what does this huge leap in potential coverage actually mean for the science we can do on Mars? If you really could have dozens of these low-cost sensors rolling potentially thousands of kilometers, like that 2,800-kilometer max range, what revolutionary questions could we finally answer? Things that are impossible now. Questions that only a swarm-traversing continent simultaneously could tackle. Think about tracking atmospheric waves or mapping huge geological boundaries over time. What discoveries might be out there just waiting for a rover that doesn't need to stop for fuel, doesn't need complex repairs, it just needs the wind to blow?
That's the million-dollar question, isn't it? Or maybe the multi-million-dollar question, even if the rovers themselves are cheaper. It genuinely changes the scale of what we even think of as planetary exploration.